This is Knowledge Engineering with Semantic Web Technologies. This is Lecture 3, Ontologies and Logic. Today we want to talk about how to mechanize reasoning and about a reasoning algorithm which is called the Tableaux algorithm. And this is part 6 of the current lecture. So first of all, let's recall. So how to mechanize reasoning. So first of all, we know a logical formula F is a logical consequence of a theory, which is nothing else than a knowledge base T, if all models of T are also models of F. And you remember model means an interpretation which computes to true. The problem here, if you have to consider all possible models, is we have to consider all possible interpretations. And this, of course, could take some while. For example, if we have infinite many interpretations, it would take forever. So how do we do this in practice? In practice, you are doing this usually with the help of a so-called calculus. So you try to break down semantical logical consequence to syntactical logical consequence, which forms a calculus, and then this has to be proven, of course. So what we do is logical consequence, so you know this entailment sign, is implemented via syntactical methods. And with this, we do define a calculus. And for the logical calculus, of course, the reason why it holds is that we have to prove first the correctness and also the completeness. So for the correctness, we have to show that every syntactic entailment, of course, is also a semantic entailment. And vice versa, for completeness, we have to prove that all semantic entailments are also syntactic entailments. Of course, in the course of this lecture, we do not prove that, but nevertheless, we keep this in mind because the algorithms that we learn are nothing else but syntactical methods to prove the correctness of logical consequence. And therefore, for all these methods, for all these algorithms that we are talking about, especially then for the Tableaux method, first, it has to be proven that the method is correct and it's also complete. But this has been done outside the scope of this course. Okay, another basic principle is the so-called proof by refutation. So what you often do is you follow the following idea to check the consistency of a logical formula. What we do is we switch the problem to its inverse and we show that its negation is a contradiction. Simply because most of these algorithms that we are talking about are able to show contradictions and not vice versa. So therefore, we are using them as a means that do proof by refutation and that are using this basic principle. So let F be a formula and T a theory, then instead of showing that if we connect or if we include the formula to the theory and show whether we can entail that this computes to true, so then this is in tautology, we simply show that if we connect the theory T, or if we combine it with the inverse, so the negation of our formula that you want to prove, this entails a contradiction, or this then in the end shows that this does not hold. So this is proof by refutation. And the algorithms for automated reasoning that are based on proof by refutation are first the resolution. We will talk about the resolution algorithm not in the course of this course, but if you are interested in, there is an extra part at the end of the course. This is extra 3.12, where we will talk about shortly about resolution. And the other one is the Tableaux algorithm. So this is the main algorithm for automized or mechanized reasoning in this course. And we will talk today in 3.6 and also in 3.9, where we apply Tableaux algorithm to description logics. Okay. So what else do we need before we get into the algorithm? We also have to talk about so-called logical equivalences. So logical equivalences, sure, you can, for example, change here if you are using conjunctive operators or disjunctive operators. You can simply change here the order of the arguments, and this is called the commutativity. So simply change f and g, which is connected by one connector or by one logical operator. This means commutativity. Another thing is, of course, you can express implication or equivalence via other connectors. So the implication of f and g is nothing else but the disjunctions of not f and g. And you can prove this, of course, again with the help of truth tables. And if you want to get rid of equivalences and implications, you can simply use these equivalences that you see here. So for example, here f is equivalent g is the same then f implies g and g implies f. And then the implications, of course, can be substituted via the disjunction, and then you don't have implications and equivalences within your formula. Then, of course, usually for applying these algorithms, usually the negation should be somehow in front of atomic expressions. For that, you have to have means how to get these negations inside, for example, braces or inside complex expressions like you see here. So in the first case, you change a conjunction into a disjunction, while of course negating at the same time both of their arguments. And these are the so-called laws of De Morgan, named after the famous English mathematician Augustus De Morgan. And then, of course, there is also the double negation, and of course, a double negated f means this is the same than a non-negated formula f. Or what you have here you have simple logical connectives with truth values, true or false. And of course, if I conjunctively connect a formula f with the truth value true, then this computes to the formula f. If I do this disjunctively, then it computes to true. And the same holds for if I compute with a logical value false. So if I do a conjunction of the formula f and false, this will of course be false. And if I do this disjunctively, this will compute to the logical formula, to the original one, to f. And of course, f and not f combines to false, while f or not f combines to true. And then you have here, if you, for example, have nested formulas within braces here, connected via different connectors as you see here, then the connector will be distributed within these so-called distributive laws. So for example, a disjunction over a conjunction will be distributed in two disjunctions over one conjunction, as you see here, and vice versa, the same with the other operators around. So in addition, we have to consider, of course, for first-order logic, the quantifiers. And for the quantifiers, as you see here, for example, it's also important to get somehow a negation which stands in front of a quantifier inside the quantifier, so inside the formula, which is bound by the quantifier and the variable. And therefore, if you do this, then of course, the polarity of the quantifier changes. So if I say for not all f, this means there exists an x for which not f holds. And likewise, if I say it the other way around, if there does not exist an x for which f holds, this means the same like for all x, it holds non-f. So this happens when you try to get the negation inside the bound formula of a quantifier. Then, of course, if I'm looking or considering the same quantifiers, then the quantifiers are also commutative. So they can be exchanged. This is not possible if I look at different quantifiers. We will see this later on. And on the other hand, also, if in my bound expression, in my expression which is bound by a quantifier, I can, of course, distribute also this quantifier over the constituents of my bounded expression. And this is the distributive law for quantifiers that you see here. So these are some logical equivalences which can be considered. And one thing you should keep in mind here, so there could exist for one logical expression an infinite amount of logically equivalent expressions that can be built, for example, with the help of these logical equivalences. So This is, of course, especially for first-order logic, of course, a rather difficult situation, and we will later on see how we are dealing with that. But now we have all the necessary prerequisites. Now we want to talk about the first algorithm for mechanized reasoning, and this is the so-called Tableaux algorithm. So the Tableaux algorithm, which is also called the method of analytical tableau, is based on disjunctive normal form. We will later learn about what this means of logical expressions. And it has been invented by a Dutch logician who is called Everett Willem Beet in 1955, and it has further been simplified by Raymond Smullyan in the form that we will also use today. So what's the basic idea of this algorithm? It's a proof algorithm. It means it's a decision procedure, and it's used to check the consistency of a logical formula by inferring that its negation is a contradiction. So this is the proof by refutation we have already talked about. So let's have a look. How does it work? So we are constructing a so-called tableau, and this tableau is a so-called decision tree, where each node is marked with a logical formula. And like you see here, a path from the root to a leaf usually is a conjunction of all formulas represented within the nodes of that path, whereas a branch of the path represents a disjunction. So we construct a tree like that. And usually this tree is constructed successively by the application of so-called Tableau extension rules, which we will talk about subsequently. And these Tableau extension rules, to build a tableau like that, they are selected from a set of available extension rules in a non-deterministic way. So what you're trying to achieve within your tableau is you're trying to close the single paths within that tree. So what does it mean? A path in the tableau is closed if along the path as well x as also not x, so in the negated form of x, if x is a formula, occurs. So x does not have to be atomic, it can also be a complex expressions. So either you have x and not x in your path, or false will occur in your path. Then this path is closed. Then a tableau is fully expanded if there are no more available extension rules that can be applied to the tableau. And if the tableau is fully expanded and if all paths are closed, then the entire tableau is closed. And if a tableau is closed, then you have a tableau proof. And the tableau proof for a formula x is nothing else but a closed tableau for the negation of that formula. So keep in mind, if you want to prove the consistency of a formula, first you have to negate it. And then if it's negated, then you can apply your Tableaux algorithm. And if the Tableaux algorithm in the end is closed, you have proved that the negation of your original formula is a contradiction, and therefore the original formula is true and is consistent. So this is what you want to check with the help of that algorithm. So of course, we are now trying to do a few examples. But first of all, I want to show you the available extension rules. And there we start with the first and the simplest version. So this is extension rules for propositional logic, so the most simple logic. Of course, we try to get rid of all possible negations. You do this, of course, if you apply the rule of double negation. So a double negated formula x will become x, not true will become false, and not false will become true. And then we are considering either conjunctive formulas, which are so-called alpha rules, which are prolonging a single path, from the so-called beta rules, which are disjunctive formulas and which are branching here within the tableau. So first, the conjunctive rules, the alpha rules. So here you have, for example, a conjunction of two formulas, x and y, and then of course you can extend the path of your tableau with x and also with y. It's the same with if you here have a negated disjunction, which computes according to the laws of De Morgan to the conjunction of the two arguments which have to be negated. So then you can extend your branch here with not x and not y. And also it's the same here with the negated implication. Then you can expand your branch with x and not y. So you can check these equivalences. So this computes, of course, to a conjunction if you're using the already known truth tables. So for the beta rules, for the disjunctive formulas, of course, x or y, they are branches the tableau in x on the left part, y on the right part. And this is the same for not x and y. So this is a negated conjunction, which again can be converted with the rules of De Morgan to a disjunction of the negated arguments. And the same is also here for the implication x implies y. This can be via logical equivalences transformed to not x or y, and then you have again here a branch or a disjunction in your tableau. Okay, so let's keep that in mind, and now let's try a very first example. So here we have, for example, a propositional logic formula. So this is an implication of first we have a conjunction, then we have a disjunction, then we have also one of the variables negated, and we want to check whether this is consistent. Of course, we could do this in propositional logic with the help of truth tables, but you agree that, of course, the longer the formula is, the longer it will take, of course, to do this with the help of truth tables, because you have to take into consideration all possible assignments to these to the logical constants you have here, or you want to represent here within that formula. Okay, so what we do is we try the Tableaux algorithm, and remember, it's proved by refutation. Therefore, in the first place, we have to negate the entire formula. And we see this is a negated implication. Therefore, we can imply here one of the alpha rules and can extend the tableau, which starts here with the entire formula, with a branch with x and not y, which means we have here the very first part, q or r, and we extend it also here with the next part, which is not, and then not q or r, and there we apply the laws of De Morgan to that small formula, and then we come to q and not r. So usually we are writing that in the way that we are numbering the single rows of the tableau, and of course after each number we write which rule we apply and on which original number from the tableau, on which row we apply the rule. So, okay, so this was the first application of the alpha rule. Next, of course, we can take into consideration again the alpha rule for conjunctions, because we have here conjunctions within our tableau. So first of all, let's have a look at row number 2. There we have q and r. Therefore, we can apply here again the alpha rule on row 2, and we can extend the tableau with q and r. So simply because it was a conjunction. Okay, nothing else. So let's go on. Let's consider the third row in our tableaus. There we have q and not r. And of course, we can apply the alpha rule here. Then we compute, or we extend the tableau with row number 6, which is q, and row number 7, which is not r. And you see here, if you look up the branch here, we have two variables here, or two formulas, which are once negated and once not negated. So we have here r and not r, and of course, therefore, this path is closed. Moreover, not only the path is closed, the entire tableau is closed, because we cannot apply any more extension rules. So you see, it's as simple as that. You have closed the tableau, which means the basic formula here was a contradiction, and our original formula, so the not negated formula, is consistent. So this is what we wanted to show. Okay, let's have a look at a more complicated example where you do not see right from the start whether this holds or not. So here you have lots of, as you see here, implications. So yeah, it's implications. And to show that, of course, or to show the consistency, we have to negate it. And then we have a negated implication, which again is an alpha rule. So we extend the tableau with the first part and the last part of the implication we see here. While the first part, of course, is unnegated, and the second part here is then negated. Okay, let's continue. First, again, same rule here, for example. So row number 3 can be also extended with the alpha rule. So here we can extend it first with the first part of the implication, and then with the negated second part of the implication. Okay, if we want to apply again the same alpha rule, we can apply it on row number 5. So here we have P and not R in the first branch here of our tableau. Okay, so on number 5, no more extension rule can be applied. So we have to consider another rule, and we have to apply this rule then, of course, on another row. And we start here with row number 2, because row number 2 holds an implication which is not negated. This means we have a better rule. And therefore, first part of the branch has to be none, or the negated part of the implication. And then the second one has to be the original second part of the implication, which is non-negated. So you see here we apply better rule on row number 2, and we have on the right side not P, and we have on the left side Q implies R. The nice thing is on the right side we see already, okay, this path cannot further be extended simply because it's closed. We have P and not P there. So we consider now the second branch here. So the second branch will be, we will follow number 9. Number 9 is also an implication. We use, of course, the same beta rule here, and Q implies R will become, on the one hand, not Q as number 10, and then, on the other hand, R as number 11. And here we see again, okay, we have to consider another branch here, and we have to consider number 4. We have also P implies Q, and if we apply here the beta rule, we come to not P number 12 and Q number 13. So this is beta rule applied on row number 4. And now we already see here, of course, P and not P is here in 2 branches. Of course, this branch and also the first branch, we already have talked about that, will be closed. Okay, let's have a look at some other branches. So this one here, R and not R, they are closed. Okay, one branch left, Q and not Q. Yeah, all branches closed. No more extension rule to be applied. And this means the tableau is closed and the original unnegated formula holds and is consistent. So you see in propositional logic, tableau algorithm is quite simple. So you simply follow straightforward the algorithm, whereas the selection, which rule you apply, is in this is arbitrary. So you can do this by random. So there is no rule which rule of the extension rules you should apply first. So this is somehow non-deterministic. Okay, if we extend this now in the end to first-order logic, as in first-order logic, we have to take into account arbitrary formulas. But here, of course, it's first-order logic formulas, x and y. And of course, for first-order logic, we have to take into account the quantifiers, which are the existential quantification and the universal quantification. And we have 2 new rules, the gamma rule for universally quantified formulas and the delta rule for existentially quantified formulas. You see them here in the 2 tables. So first let's have a look at gamma, which is the universally quantified formula. So if we have a universally quantified formula, then we can simply substitute the variable over which we quantify with an arbitrary ground term. This means a term that does not contain the variable that is bound in our bounded expression phi. So you can take an arbitrary one because the assumption holds for all possible. Usually you are looking there for some expression that already exists within your tableau because simply you want to find here the contradictions on the same variable, of course. On the other hand, if you look at existential quantified formulas, there you can substitute the variable within your bounded or the bounded term that is bounded by the existential quantification with a new constant, simply because you say, yeah, there should exist some expression where that holds. And this not necessarily already exists within my tableau, but there is something, it exists, so I create a new constant for which exactly this assumption holds. And you see here in the 2 tables, of course, this holds on the right-hand side in blue for the universal quantification, but also for the equivalent the equivalent negated existential quantification. So therefore you have two rows on each side in the table. Once it's for the original quantifier, and of course it's for the inverted negated quantifier also. And the difference between the two rules means for universally quantification, use an arbitrary ground term, and for existential quantified formulas, use a new constant if you try to apply it. Okay, in the end, let's have a look at a small example. So here you have a longer formula, a first order logic formula, which contains, of course, universal and existential quantification. So let's have a look at that. If we want to prove that, of course, first we have to negate it. And then, of course, we see it's a negation of an implication of quantified formula. So in the very first place, we can apply simply the alpha rule because it's a negated implication. And of course, then here we have the first part non-negated and the second part negated. And this then, of course, are, as we see here on the first hand, number 3, it's a negated disjunction where we can also apply an alpha rule. So this can then be translated in the following way. It means the branch of our tableau will be extended by the first part of the disjunction, which is of course negated, and then the second negated part of the disjunction. And there, of course, in row number 4 and row number 5, then we have to apply definitely one of the new rules, new extension rules, either the gamma or the delta rule. Okay, so let's take first into account number 5, because number 5 is an existential quantification, simply because it's a negated universal quantification, which is an existential quantification. Therefore, we can substitute x here, or the quantified part of the bound part of that formula, by the constant c, which is new. So this will be then, or we can extend the tableau with non or negated q of c, because it holds because there must exist some constant for which not q holds, according to 5. Okay, what we do next, of course, we are looking at 4. In 4, you see here a universal quantification, of course, disguised as a negated existential quantification. And therefore, we can here substitute the bounded part, or the variable x, simply by an already existing ground term, which does not contain x. And therefore, we take, of course, the variable c, which already exists here. Because this should hold for all, then, of course, it should also hold for c. So therefore, this becomes not, or p of c, negated. Okay, what can we do next? We can apply the gamma rule to the second row that we see here. And in the second row, we have a universal quantification over a disjunction. And therefore, of course, it's a universal quantification. We can substitute the variable x by, again, an arbitrary ground term. We choose, again, of course, c, because we want to be able to deduce a contradiction. And of course, we are allowed to do this because it's a universal quantification and it must hold for all. And c, of course, is a constant, so it does not contain the bounded variable. So the result here will be p of c, then disjunctively connected with q of c. Okay, and this is a disjunction. We can apply the beta rule, and therefore on the first half of the branch we have p of c, and on the second half we have q of c. And we see already here that, of course, we have p of c and not p of c in the branch, and also in the other branch we have q of c and not q of c, which means again here the tableau is closed, which means that the originally non-negated formula is true, so it holds. So this is an example for applying the Tableaux algorithm for first order logic. Of course, it's difficult or more difficult than for propositional logic simply because you have to take into account the quantifiers. Sure, but we will do this in the exercises and you will definitely learn how to do that. Okay, so far with first order logic, we have shortly spoken about that first order logic is rather expressive. And sometimes it's also too bulky, it's too large, simply because of this property that it's only semi-decidable or not decidable. Therefore, we are looking for something else for knowledge representation. And we will see in the next part of the lecture that the most suited part for knowledge representation and for our purposes will be the so-called description logics.